Hello, welcome to my coronavirus classroom. I'm Janessa Jacobs, and this is the autonomic nervous system. I actually could not find my big boss teacher version of this lecture, so I'm going with the student version, which actually works because then I didn't have to delete all the pictures. So, the autonomic nervous system is, in my opinion, the most important system for getting you through next semester. The autonomic nervous system is automatic, and it controls everything that you're not thinking about. Cardiac muscle, smooth muscle, glands. So it's horribly, horribly important, and literally everything we talk about in the second semester is going to be controlled by the autonomic nervous system. That's why I end here instead of the special senses. So the autonomic nervous system is the branch of our peripheral nervous system that is automatic. We don't think about it. The somatic division of the peripheral nervous system is where we have control of our skeletal muscles. But here, this is all automatic and we're not thinking about it. It happens below our conscious regulation, and that's good because we don't want to have to think about pumping blood through our blood vessels and then adjusting which blood vessels and which organs get which blood when. We don't want to have to think about that. We want to automatically handle it lower down than the cerebrum, which is doing all the things like thinking about taking notes in class or thinking about teaching a class. So, to begin, our autonomic nervous system consists of motor neurons that are going to innervate smooth muscle, cardiac muscle, and glands. So, autonomic nervous system, or the ANS, this is the abbreviation I'll be using from now on, consists of motor neurons that innervate glands, and then we could say cardiac and smooth muscle tissues. Okay, so it's autonomic, it's automatic, you don't have to think about it, it just runs, which is great. So the first thing this chapter does is kind of compare your autonomic nervous system to your somatic nervous system. And they both have motor fibers, but those motor fibers are going to differ in their effectors. We just talked about that. So there must have been more I was supposed to say on that when I saw the slide. Autonomic nervous system consists of motor neurons that innervate our glands, cardiac muscle, and smooth muscle. I guess another thing that I could say is ensure optimal support for a changing environment. And we'll describe how as we move through our lecture today. Okay? Alright. So both have motor fibers, so somatic is going to be the division that you have control over. So those motor fibers are synapsing onto effectors that are skeletal muscles. The autonomic nervous system is synapsing onto effectors that are our cardiac muscle, smooth muscle, and glands. So both divisions have motor fibers, but they are going to differ in their effectors. So, for our autonomic nervous system, since it's here on the left side of my board, we'll say our autonomic nervous system innervates cardiac muscle, smooth muscle, and glands. And my somatic nervous system is going to innervate skeletal muscle. Skeletal, yeah, I got it. You have to forgive me. I have skeletal muscles in my neck pinching down and hurting and giving me this big old headache. Okay, so both have motor fibers, but they're going to differ in their effectors. Autonomic nervous system has the effectors, cardiac muscle, smooth muscle, and glands. Somatic motor system, somatic nervous system, has our motor neurons that are going to innervate our skeletal muscle. So another difference is the neurotransmitters that are used. In the autonomic nervous system, we're going to use two neurotransmitters, acetylcholine and norepinephrine. our somatic nervous system, we are only going to be using acetylcholine that we met coming from our lower motor neurons that we're going to read in our skeletal muscles, right? Give me one moment. Okay, so not only do we have different effectors and neurotransmitters, but the effects of those neurotransmitters at the effectors are going to be different. Acetylcholine is always stimulatory at skeletal muscles, so that's the difference we could say. ACH is always stimulatory at skeletal muscle. It's not very often that we can make an always statement, but we can say that here. Anytime I dump acetylcholine on the motor end plate of a skeletal muscle, it will be excitatory. And it's going to stimulate that muscle to ultimately contract. Okay? Now, our neurotransmitters in the autonomic nervous system are going to be able to have inhibitory or stimulatory effects depending on the receptor type they're binding. So that's going to be a difference. We could say that our neurotransmitters in the autonomic nervous system can be stimulatory or inhibitory depending on the receptor at the target. So that's going to be another big difference. So our motor fibers are going to differ in the effectors that they're landing on and the neurotransmitters that they're releasing. Another difference that they have is in our somatic nervous system, we had one lower motor neuron that synapsed onto our effector, the skeletal muscle. In our autonomic nervous system, we are always using a two motor neuron chain, a preganglionic neuron and a postganglionic neuron. Okay, so that's going to be another difference between our autonomic nervous system and our somatic nervous system. So for our somatic nervous system, what we could say is that it uses one lower motor neuron, which is going to synapse onto the skeletal muscle. Okay, our autonomic nervous system has two divisions, and the arrangement of their two motor neurons is going to be different in each division. So that's the nitty-gritty that we're going to. But just be aware, as a general rule, what we could say in the autonomic nervous system is that we have a two motor neuron chain. And the two neurons are what we call a preganglionic neuron and the postganglionic neuron, or the ganglionic. Some books call it the ganglionic neuron. I am going to call it the postganglionic neuron. Okay, so we differ in our effectors, we differ in our neurotransmitters, and then we differ in this like lower motor neuron ganglia arrangement. And then we're going to even differ in here when we get to the two different divisions. So let's look at this in a little bit greater detail. We could say that the effectors in the somatic nervous system are what? Skeletal muscles. The effectors in the autonomic nervous system are what? Cardiac muscle, smooth muscle, and glands. Effectors, ANS. We're going to sum it up. Our cardiac muscle, smooth muscle, and glands. Guess what we're talking about? First things first next semester, glands. Then next, we'll talk about the cardiovascular system. We'll talk about the other systems. So, horribly important. Somatic nervous system, effectors, skeletal muscle. The only thing you have voluntary control over. Okay? Efferent pathways and ganglia. So this is going to be another difference. So what we'll see in the somatic nervous system is that we've got some upper motor neuron that's arising from where? The precentral gyrus of your frontal lobes, right? So this is my upper motor neuron, and it's synapsing onto an unnamed interneuron, or the lower motor neuron that is extending out and synapsing onto some skeletal muscle. Okay? So for my efferent pathways and ganglia, ganglia is where cell bodies gather outside the CNS. For my somatic nervous system, I don't have a ganglia. Where were the somas for my motor neurons in my somatic nervous system? cord and synapsing onto the skeletal muscle. What I see in my autonomic nervous system is that I've got my preganglionic neuron is going to arise either from the craniosacral division of the spinal cord or the thoracic and lumbar division of the spinal cord and go out and synapse onto my second motor neuron, my postganglionic neuron, and that is going to be the one that is having the effect of the target. So that's going to be the difference between my between my autonomic and somatic nervous systems is my efferent pathways and ganglia. Ganglia, groups of cell bodies outside the central nervous system. So I don't have ganglia in the somatic nervous system. My cell bodies are found in the ventral horns. In the efferent pathway for my autonomic nervous system, I'm finding these my preganglionic neurons. They are here in the lateral horns of my thoracic spinal cord that's leading out to my thoracic spinal nerves, which are going to contain my postganglionic neurons. So the ganglia is the group of those cell bodies, and if you recall when we were looking at the spinal cord, if you looked right outside it, we said we had these dorsal root ganglia. Well, if you recall, that was going to meet up with our motor neurons where we're going to become a spinal nerve and go out. Well, now what happens in our thoracic nerves is those thoracic nerves that the nerves that are arising from the thoracic part of the spinal cord are going to be able to branch into another ganglia, either right here in the sympathetic nervous system, just outside the vertebral column, or in a ganglia at the target organ. So that's important to be aware of. The cell bodies for our somatic nervous system, lower motor neurons, were all in the central nervous system. The cell bodies for our autonomic nervous system are going to be found either in the central nervous system, if they're that preganglionic neuron, or in the ganglia, if they're the postganglionic neuron. And we'll look at the differences between the two divisions of this in a moment, but just be aware of that. I hope that made some sense. Okay, my autonomic nervous system. I'm using acetylcholine, and again, this is going to be stimulatory or inhibitory, depending on the receptor, and we'll talk about that in a moment. And then I'm going to be using norepinephrine in my sympathetic nervous system, only at targets, and this again will be stimulatory or inhibitory, depending on the receptor at the target. The neurotransmitter effects of in the somatic nervous system is that acetylcholine is always stimulatory to a skeletal muscle. Wonderful. How do our somatic and autonomic nervous systems overlap? Well, both divisions can be overridden to some degree by higher neural centers. So imagine you're in an autonomic nervous system fight or flight situation. You're having a panic attack because you just heard some really loud noise in your house. So your sympathetic nervous system takes over and your heart starts racing. But if you think about it, you realize, oh, that was just a book dropping on the floor. I don't have anything to be scared of. Then your your cerebrum can take over and kind of slow it down. So both can have cerebral input. So we could say they're both affected by cerebral input. Where else would they overlap? I mean, lots of places. Like if you're in an autonomic nervous system fight or flight situation and you need to be punching someone, then it's your ability to control your somatic muscles that are helping you to do that. Other things in a sexual response. So your autonomic nervous system is going to be controlling what's happening in the reproductive organs. Your somatic nervous system is going to be absolutely necessary to engaging in the behaviors that lead to the sexual response. So there's overlap. Okay, so we have two arms of the autonomic nervous system. the sympathetic nervous system, which controls fight or flight functions, and the parasympathetic nervous system, which controls rest or digest functions. And I'm not going to write that down on this slide because look, role of the parasympathetic division. This is going to be the division of the autonomic nervous system that is responsible for like growth and maintenance and healing and resting and recovering. So you'll see it often termed rest and digest. And the role of the parasympathetic division is to maintain homeostasis at rest. What does that mean? That means I need to do like rowing, I need to do maintenance, all that stuff. If I am resting, then I can be taking these nutrients, digest them, and use them to fuel growth if I'm growing, or maintaining whatever it is that I'm doing throughout the day. So, yeah. Parasympathetic tone, if we think about muscle tone, a slight level of contraction. The parasympathetic division is really kind of in control of what's going on in your viscera, in your guts, and helping to keep your like normal resting heart rate and things like that. So, resting respiration rate. Your heart sets its own pace. We'll talk about that next semester. But in general, the parasympathetic nervous system, or the PNS, I'm from now on, in the rest of today's lecture and in your review of this chapter, I'm going to abbreviate the parasympathetic division of the nervous system as the PNS. And you might say, yeah, but we use that for peripheral nervous system. And I'll say, I probably didn't, because every time I use the abbreviation PNS, I'm talking about the parasympathetic nervous system. Why? Because every time I use the abbreviation SNS, I'm talking about the sympathetic nervous system every time. Like, I would never use SNS for the somatic nervous system. I just wouldn't. Why? Because everybody calls the SNS the sympathetic nervous system. So the sympathetic nervous system, or the SNS, the sympathetic division of the autonomic nervous system, which is a division of the peripheral nervous system, is the system that's in control of fight or flight. And so what does it do overall? It prepares your body for emergencies, or like high energy situations. So when you're exercising, this system will kick on so that we can shunt our blood to our skeletal muscles and away from our digestive organs, where we don't need to be resting and digesting because we're exercising. Okay? So, great. These are the two divisions we're going to look at. Really what the sympathetic nervous system does is help mobilize you for an emergency. So you've probably heard situations where a, somatically strong woman, such as myself, could lift, the 45, 50-pound barbell, but what about the car off of the child? A woman my size could lift a car off of a child because of what happens when the sympathetic division is activated. So what it does is it really gets your body into like superhero mode. It's quite phenomenal. So it prepares your body for emergency situations or an increase in energy usage. And if you're saying to me right now, I cannot read that, I would say this is exactly what happens in class, and what I tell my in-class students as I'm telling you, you're in class. My face-to-face students that I'm telling you is someday you're going to have to read Dr. Chicken Scratch, and it's going to look less legible than that. So what this sentence says in Dr. Chicken Scratch is prepares body for emergency or increased energy usage. Okay? Perfect. Extra lesson you got in the coronavirus classroom today. I will try and be slightly more legible as we move throughout lecture. So, if we look at the two divisions of our autonomic nervous system, they're going to have three main anatomical differences. Our parasympathetic nervous system is going to arise from cranial and sacral nerves. Our sympathetic nervous system is going to arise from thoracic and lumbar nerves. Okay, a second anatomical difference is going to be the location of the ganglia. I don't know if this is the same order as your book, but I also don't care because it's one of the three. So, for the ganglia in the parasympathetic nervous system, these are at or in the wall of the target organ. Oh, this is actually probably the last, but at least to this second, which is why we're okay going with it. In the sympathetic nervous system, the ganglia is in the sympathetic trunk, or the sympathetic chain. And what it is where you have these preganglionic neurons meeting with the postganglionic neurons right there. So, anatomical differences, structural differences. The rest and digest system has the ganglia, which is where we've got our cell bodies, at or in the wall of the target organ. Our sympathetic division has the ganglia in the sympathetic trunk, which is just outside the vertebral column. Then if the location of our ganglia is a difference, then the other anatomical difference is going to be the length of our pre- and postganglionic neurons. So, imagine this. I have to go all the way, let's say this is my heart, and my ganglia is at or in the wall of that organ. Then my postganglionic neuron is going to be really short. And the preganglionic neuron that's going to extend from my central nervous system away to that is very long. Okay? And in my sympathetic system, if I have my ganglia in the sympathetic trunk, which is just outside the vertebral column, then that must mean I've got a short preganglionic neuron and a really long postganglionic neuron. So that's the third anatomical difference, we could say, is the size or the length of the pre- and postganglionic neurons. So, in the parasympathetic nervous system, we have long preganglionic neurons synapsing on our postganglionic neurons at or in the wall of the target organ, which means that we have short postganglionic neurons. And in my sympathetic nervous system then, if my preganglionic neuron is synapsing on a postganglionic neuron in the sympathetic trunk, my preganglionic neuron must be very short, relatively. And it's synapsing onto a long postganglionic neuron that is extending a long distance away from that sympathetic trunk to synapse at the target organ. So we've got a long postganglionic neuron, and that will be another anatomical difference. Okay? So 3 main anatomical differences, which means that I should be able to show you a figure of structures, and you should be able to determine which division of the autonomic nervous system I'm talking about. Hint, hint, most of your exam on this system is going to come from identifying stuff on a figure that I'm not showing you because of copyright infringement rules, but I'm explaining to you right now. Anatomy is structure. You can look at structure. If you are looking at a figure of a human body and the preganglionic neurons are arising from the cranial nerves and the sacral nerves, that is an anatomical fact that leads you to knowing that the division we're talking about is the parasympathetic nervous system. If the figure that you're looking at shows that our preganglionic neurons are arising from our thoracic or lumbar spinal cord, that is an anatomical fact that is going to lead to the physiology of our sympathetic nervous system. Okay? So I can show you a figure, or I could put a figure on the test and completely 100% test you on that figure. 50 points there, 50 points there. I won't, but mostly. It's not 50 points. This is a half a test. 25 points there, 25 points there on a figure. And I could do that based on the fact that you should be able to identify them based on 3 anatomical differences. Where our nerves are arising from in the spinal cord, cranial and sacral spine or thoracic and lumbar spine. Whether we have long preganglionic neurons and short postganglionic neurons that are meeting at the ganglia at or in the wall of the target organ, or whether I have short preganglionic neurons and long postganglionic neurons that are meeting at the ganglion in the sympathetic trunk. Anatomy leads to physiology, people, and even if you can't see it yet, the anatomy is going to allow you to distinguish the difference in these systems because they have very different physiology. We just talked about the fact that the parasympathetic nervous system is in control of rest or digest, maintenance, growth, normal stuff. Sympathetic nervous system is not normal. You're in a stressful situation if you're fighting or fleeing, but your body can do it. And in that situation, we are going to need to activate you, get lots of glucose on board so that you can be thinking your way out of this, and so that we can be like exercising, well, not like if you're actually in an emergency, fighting or fleeing our way out of this. And exercise is a little different, but it's also the same. We need to be shunting our blood to our skeletal muscles and things like that. So those are our anatomical differences. Now let's look at the ways that our physiology works to allow us to respond to all kinds of environmental situations. Okay, so your parasympathetic division is also called the craniosacral division, and that's because the fibers originate from the brainstem, where our cranial nerves are coming out, and our sacral regions of the spinal cord. So it's our craniosacral division, and so the figure probably that is in your book right here is probably pretty generic and showing you like, oh, and there's our spinal cord, and so our nerves for this division are coming out here and out of here and getting our targets. Okay, our sympathetic division is also called the thoracolumbar division, and that's because our preganglionic neurons are arising from the thoracic and lumbar nerves. Again, forming the lateral horns of the spinal cord. We talked about that earlier. So the figure in your book that you're probably looking at then has for this division. Okay? And what we're going to, but it's like going up. And because we're coming to all of our targets. So here are our targets. And here are our targets. Okay? Whoa, that's what you're looking at. That's all these slides are showing you. And I've already told you about it. Our parasympathetic division arises from our cranial and sacral nerves. So it's also called the craniosacral division. Okay? Our sympathetic division is also called the thoracolumbar division. And that's because we are arising from our thoracic and lumbar spinal cord. Okay? Cool. Great. Sympathetic division. Okay, I think I'm like trying to pull from my excellent brain that you all have too. Like, what figure is in this lecture? Because I couldn't find my teacher lecture. I just found a student lecture and I'm just going with it. So, this is great. I'm pretty sure what this is showing is like our sympathetic division and like an eyeball and some salivary glands, probably the skin, heart, lungs, stomach, small intestine, digestive tract, liver and gallbladder probably clumped together. So I think that's probably what it's showing in that figure. And then what it's trying to illustrate is that once these preganglionic neurons, let's just imagine, this is my sympathetic trunk. We'll talk about all those effects in a minute. We're gonna just like real quick like gloss over this part because you can learn this part in a neurophysiology class someday. I want to make sure when you get to that neurophysiology class, you have enough understanding that you don't feel lost. So this is too much information for a first semester A&P course to learn, but your preganglionic fibers in your sympathetic system can follow 3 different pathways into that ganglion. They can either, 1, go into the ganglion and meet their postganglionic neuron right there at the level of the spinal cord. Okay? Or they could, 2, come in and go up or down to synapse with the postganglionic neuron. So that's the second possibility. The third possibility is the worst possibility, is that, I hate it, is that you leave the sympathetic chain ganglion altogether and go to some collateral ganglion. And then synapse with your postganglionic neuron. Okay, so just be aware of that. Like in class, all I would have done is like shown you the figures and said read it, so you actually got a little bit more than in a face-to-face class by me drawing out this much. Just be aware, there are three pathways that preganglionic neurons can follow after exiting the spinal cord so that they can meet up with their postganglionic neurons. Okay? Now, one weird thing about the sympathetic nervous system is that it's actually got one part where your sympathetic nervous system can send, it only sends out one neuron, and so this would be our preganglionic neuron, all the way to this spot called the adrenal medulla. Your adrenal gland sits on top of your kidney. Your kidney filters your blood and produces urine. On top of your kidney, you've got this thing called your adrenal gland. And it's got an outer glandular cortex and an interneural modified nervous tissue medulla. That medulla of your adrenal gland releases these hormones you've probably heard of. You've probably heard people say adrenaline. Adrenaline is the layperson's term for epinephrine and to a lesser degree norepinephrine that's released from the adrenal medulla. So there's a specialization here. When you are in a fight or flight situation, this is an emergency or very highly stressful. We want to be able to kick out. Imagine, you've heard of adrenaline. What does it do? It makes you increase your heart rate. It makes you increase your respiration rate. Like adrenaline junkies love excitement, right? So adrenaline or epinephrine and norepinephrine are going to do all of these things that make adrenaline junkies excited. They're going to enhance all of the effects of the sympathetic nervous system. If you're already in a fight or flight situation, you can also get your sympathetic nervous system to activate the release of a hormone that amplifies above and beyond. And where that happens, this is a specialization. We don't have a two-neuron chain going to the adrenal medulla. Instead, what we have here is our preganglionic neuron is going to synapse right into the adrenal medulla, and it's going to bind to a cholinergic receptor and cause the release of epinephrine, which is abbreviated epi, I'll from now on use, and norepinephrine. We're going to talk about norepinephrine a little bit as a neurotransmitter. That's what our sympathetic nervous system is using in our target organs. Norepinephrine released from the adrenal medulla is a hormone. Hormones are released into the blood and can have their effect over any cell in the entire body that's got a receptor for that hormone. Neurotransmitters are released into a synapse and can only affect this postsynaptic cell across the distance of a synapse. So everything that's happening in our sympathetic nervous system is a short distance signal where we're using a neurotransmitter to cause some change in a target organ. What happens here, and what is so cool here, is that our nervous system can stimulate a gland to release a hormone that is now going to enter the blood and amplify every effect of that neurotransmitter in the body. It's super, super cool. So just be aware of that. That's what's going on in your book right now, is kind of introducing you to those different pathways. Okay? So the parasympathetic nervous system is kind of easy when thinking about the ways that its preganglionic, postganglionic chain goes, because there's nothing weird like that. We're not shooting up and down, and we're not going to collateral ganglion, and we're not potentially just innervating the adrenal medulla. Instead, with what's happening in the parasympathetic division is that our preganglionic neuron is extending a long way away to our postganglionic neuron that's right there in the target, and we're having our effect there. Alright, if you recall, somatic reflexes were those spinal reflexes that were protective for various reasons. Visceral reflexes are these kind of things that happen in the body without you thinking about it, of course, because it's viscera, but also without cerebral input. So how can we respond to a changing environment without requiring any higher brain input? And so we've got the same basic components in a visceral reflex as we did in a spinal reflex. And let me think about like an example of a visceral reflex. If you eat some really, really lipid-rich food, you're going to activate a visceral reflex that's going to cause your gallbladder to release bile, because bile salts help with fat digestion. You're not thinking about that, but it's happening. And so it's a visceral reflex because it's a reflexive activity which does not require your cerebral input or your central nervous system input and it's happening in the guts. We're not thinking about it. So we'll go over these more next semester, but right now we can still know the generalities. So for a visceral reflex, we have some kind of stimulus. Actually, for this stimulus, let's say, or for this example, let's say the stimulus is an increase in stretch. Stretch of what, lady? Let's say my blood vessels. So if my blood vessels stretch, what that's telling me is my blood pressure is going up. So if I get a stretch in like my aortic arch, that is indicating that I've got an increase in blood pressure, and I'm going to have to be able to come back to homeostasis. So the stimulus would be an increase in stretch or an increase in blood pressure. This is going to be able to affect or stimulate some receptor. Have an effect on a receptor, which is to say, hey, there's a change. You might say, wait, I thought the effector was at the effector. The effect is at the effector. You might be having an affect at the receptor. And if you are a change in some external variable, that's what you're doing. You are affecting the receptor. You're causing it to change. Change what? Detect a change and tell the sensory neuron. Right? And the sensory neuron is going to communicate that back to an integration center. And that integration center is going to communicate through a motor neuron that's going to talk to an effector. The difference between a visceral reflex and a spinal reflex is that now we have a two-motor neuron chain all caught up here in this integration center. We've got our preganglionic neuron that's synapsing onto my postganglionic neuron, and my postganglionic neuron is synapsing onto my last part of the system, the effector. And now my effector is going to be cardiac muscle, smooth muscular glands, and what's going to happen there is going to depend on which branch of the nervous system I'm talking about and what organ I'm talking about. What neurotransmitter is present, what receptor is present. It's a hot, massive autonomic nervous system. You're going to love it. Okay. Man, could you hear? No, I don't have my microphone on. You couldn't hear all those creaks of my old knees that I could hear when I bent down to pick up that microphone lid. Okay, visceral reflexes. Examples of visceral reflexes. Oh, reflexes that empty the rectum and bladder. Sure, we can train these reflexes, but at first, when you're a little baby, they're not trained, you're just going, okay? So what happens here is, and then the enteric nervous system is actually a 3-neuron reflex arc. We'll talk about that when we get to the digestive system. The enteric nervous system is your whole gut brain. Your digestive system gets its own brain because digestion is so complex. Your brain need not think about it. Okay, visceral sensory fibers are going to be involved in what you've heard of as referred pain. All that stuff is handled by your visceral reflexes. All right, so let's try this again. It's a different day now, but hopefully we will just make it straight through. How are we going to fit everything that we talked about already together to make a model of something that's easy to understand for a test that you have to have like tomorrow? We are going to look at
Baby Bear.
Baby Bear is going to help us look at the role of the parasympathetic division and the sympathetic division, and where we still have to go in lecture is finishing the neurotransmitters that we have, the receptors, and the effects of all of our targets. So let's just think about this. The parasympathetic division, we said, was the craniosacral division, and it was going to be in charge of our rest and digest functions. Okay, so here's your brain, here's your spinal cord. Up here, coming out of your brain, we have cranial nerves. Okay, so, and down here, we have, coming out of your spinal cord, we have sacral nerves. All right, I think in the interest of having the most repetition available in this limited amount of time so you can learn as much as possible, I'm going to tell you stuff we're going to talk about in a few slides. We're going to talk about neurotransmitters and receptors in a little bit, but we can talk about them now while we're drawing up the neurons that are releasing, or the nerves that contain the neurons that are releasing those neurotransmitters and everything that contains those receptors right now. Oh, my people, I love you. Take 9 million. Okay. So, I think I'm just going to start here and leave this picture up because it was good. And we'll see what kind of editing. I'm not going to do any editing. So, recall that the parasympathetic division we said was a craniosacral division, meaning that our preganglionic neurons are arising from cranial and sacral nerves. You don't need to worry about the details of all of the branching of that because it's kind of complex. Someday if you need to in a neurophysiology class, you'll know that. What you do need to know is that we've got long preganglionic nerves containing these long preganglionic neurons that are extending a long way away to the ganglion at or in the wall of the target. So a ganglion, what's a ganglion? It's a group of cell bodies outside the central nervous system, right? So, okay, what cell bodies would we see then? What we find at the ganglion is the somas of all of our postganglionic neurons. Okay, so at my ganglia, we have, the reason it's a ganglia is because we've got a lot of cell bodies there. So we've got our somas of our postganglionic neurons. And okay, so those are, the ganglia is at or in the wall of the target organ, which means that our postganglionic neurons are very short. They're extending just a short distance away to synapse on their target and have their effect. Okay, so wonderful. Well, that means that we have really long preganglionic neurons that are extending away from my cranial and my sacral nerves and synapsing on those postganglionic neurons in those ganglia. I think I got that. So, long preganglionic neurons synapsing onto short postganglionic neurons that are then having an effect on the target. Okay, so the vagus nerve is what I had drawn here and lost in the last video. The vagus is awesome. Cranial nerve number 10, it's the wanderer. It exits the neck, it wanders all the way through, and is going to be able to affect your viscera, your guts, all the way down in your abdominal cavity, from all the way up here in your brainstem. So that's it shoots out really long neurons that are going a very far distance to synapse on the postganglionic neuron at the autonomic ganglion, which in the case of the parasympathetic division is at or in the wall of the target. So our ganglia, at or in wall of the target. My postganglionic neurons are short. My preganglionic neurons, which are arising from my cranial and sacral nerves, are long. And what I'm going to just talk to you about right now and bring into play right now is neurotransmitters and neurotransmitter receptors. I know it's at the end of the lecture slide-wise, and it just seems like it's going to be easier to go this way. So we're doing it this way anyway, and then when we get to those slides, we can review it. So, neurotransmitters are the chemicals that are released by our neurons, right? Yes. So all of our neurons, preganglionic and postganglionic neurons, are neurons. They've got somas, they've got axons, they've got axon terminals, and those axon terminals are storing neurotransmitter. Okay? So in the parasympathetic division, all of my preganglionic neurons are what we call cholinergic neurons. They are making and releasing acetylcholine onto postganglionic neurons. Okay, so in my parasympathetic division, my preganglionic neurons are all cholinergic, meaning that they produce, store, and release acetylcholine. It's the same kind of acetylcholine that you met at the neuromuscular junction. And the thing about it here is that it's going to cross the synapse and bind to the receptive segment on our postsynaptic neurons, which are the postganglionic neurons that are short, and these are also cholinergic neurons. Okay? Meaning that all of these short little postganglionic neurons are producing, storing, and releasing acetylcholine into the synapse, and now it's crossing, and instead of binding the receptive segment on a neuron, it's going to bind to a receptor on the target. And the receptor on the target is going to determine the effect. Okay? So we'll come back to neurotransmitter receptors maybe in lecture. That'll make sense. Because now what we should talk about is the effects at all of our targets. And then we'll do a similar comparison for or the similar breakdown for the sympathetic division. So what was the other thing that we said is that anatomically difference-wise that we're going to be using different neurotransmitters and different neurotransmitter receptors, so we'll get there in a little bit. Right now, in our parasympathetic division, we are only using cholinergic neurons, which means that our postganglionic neurons have cholinergic receptors, and our targets have cholinergic receptors. We'll get there in a minute. The effects of those receptors at the targets can be inhibitory, stimulatory, depending on the receptor subtype at the target. At the target, at the end of the day when we get to our organs. So what's happening at all these organs? Well, our parasympathetic division is in control of rest and digest. It's a very secretory, juicy thing to do digestion. So you can think about it as generally being secretory. So if we look at our targets, well, we already talked about one target when we were looking at our special sense of vision. And we said that when we were in a rest or digest situation, what happens to the pupil? Does it dilate or constrict? In rest and digest, it constricts, and we could like focus on reading a book, right? Right? And then in fight or flight, it dilates in an emergency situation to allow in as much light information as possible. Okay, so we'll get there in a minute. So that's one thing we could say that the parasympathetic division does, is at the pupil, it's going to stimulate pupil constriction. Okay. At the lacrimal glands, at the nasal gland, in the nasal mucosa, at your salivary glands, all of that stuff is juicy. So we'll stimulate their secretions. So we can stimulate lacrimal and nasal secretions. And these little guys here, believe it or not, so there's an eye, this is the nose, that's the nasal cavity, see those are your nasal concha, and this is your mouth, where we're, your oral cavity, where we're going to be stimulating our salivary glands as well. So we stimulate our salivary glands. Okay, now at the heart, when I'm in a rest or digest situation, it's not like you're just sitting around because your heart sets its own pace, which is really cool, and you'll get to learn about next semester. But it's not like you're just sitting around at rest, your resting heart rate, and then all of a sudden your parasympathetic nervous system kicks on and is like, we need to go lower. That's not what happens. What happens when your parasympathetic nervous system kicks on at your heart is that your heart rate has been increased above and beyond normal resting heart rate, and now we need to bring it back down. So let's imagine that I heard a car backfire outside and my heart jumped. Well, everything jumped, but my heart rate increased because I got scared. As soon as I realized that it's not a gunshot, it's a car backfiring, then my parasympathetic nervous system can come back down or can kick in and bring my heart rate back down to rest, and then my heart will take over what it does. But if we needed to think of an effect here of the parasympathetic division at the heart, it would be like, it's kind of inhibitory, because what it's doing is we're decreasing our heart rate. Okay, and this is going to be a difference. The parasympathetic division can only have an effect on heart rate at the heart. The sympathetic division can have an effect on force too, not here. So that's going to be a difference, probably more important next semester, but look, all this stuff is important next semester. That's why we're talking about it now. Parasympathetic division decreases heart rate. At your lungs, when you're resting and digesting, we could also decrease our respiratory rate. And we would do bronchoconstriction. Okay. All right, so that would be the effect at the lungs. This thing, believe it or not, right here is a liver, and this is the gallbladder. When you're resting and digesting, there are going to be a couple things that the liver and the gallbladder can do. Your liver produces this stuff called bile that gets concentrated and stored in the gallbladder, released into the small intestine, and that helps with lipid digestion. So all stuff we're going to talk about next semester. That's why it's important to review this part of 201 right now. So, okay, great. That's one thing that we can do when our parasympathetic division is involved, is we could stimulate our production of bile and release. We're going to do reflexes all through the enteric nervous system, the gut brain, that will really control bile secretion, but we can get the secretory process going because of parasympathetic division input. The other thing that we can do is we can stimulate the liver to take all of this. If we're resting and digesting, then in theory we should have some nutrients passing through here. So the liver can take the nutrients that are coming in, and let's say if we have an increase in glucose, we can store that as glycogen. So at the liver, we would stimulate what's called glycogenesis. Genesis, to make what? Glycogen. Glycogen is our storage form of glucose. So when we're in a rest and digest system, we can stimulate glycogenesis at liver tissue. Okay? What else? This is the pancreas. And again, your pancreas is going to be juicy. It secretes digestive juices, pancreatic juice, into the small intestine, which is going to help with digestion. It's also involved in blood glucose regulation. We'll talk more about that next semester, but you could just think when we're in a parasympathetic rest and digest situation, we will stimulate the pancreas to secrete. So we're stimulating the secretion of all this stuff, release of all this stuff to do what? Get into our guts, at the stomach. Where's my stomach? I don't have a stomach up here. So at the stomach, we could say that we're also going to stimulate secretion of gastric juices, but also motility. And that is going to be the same for our intestines. Maybe I should have just drawn it down here with intestines. So at the stomach and intestines, we will stimulate secretion and motility. Motility is movement. So it's going to vary from organ to organ, and there's a lot of nitty-gritty detail that we really are going to spend an inordinate amount of time talking about next semester. So the point is to get you to see how your nervous system is controlling everything next semester. It's autonomically and against your will. So what's happening here when you're in a parasympathetic situation is like in your small intestine. You're going to start secreting brush border enzymes. You're going to have segmentation. You're going to do peristalsis. The other thing that the parasympathetic nervous system does, if you look down at like the bottom of that figure, you'll see that it's showing the like sigmoid colon, the rectum, the anus, and the urinary bladder. Micturition or urination and defecation are reflexes that are controlled by the parasympathetic division. So you could say that this division is stimulatory for urination and defecation. And you might say, yeah, but wait a minute, I thought this was rest and digest and that sympathetic nervous system was fight or flight. I've had the crap scared out of me, lady. Well, that doesn't mean that your sympathetic nervous system was stimulating your reflex. What it means is you lost parasympathetic control. And so you lost control, yeah, because you were like that, yeah, so that's why I got scared out of you. So sympathetic nervous system is not involved in the stimulation of those reflexes. The parasympathetic division is, okay? It's juicy, it's secretory. Juicy, urination. Secretory, excretion. I promise it's happening. Believe it or not, this is male genitalia and this is female genitalia. I was trying to figure out how to draw that with my 4-year-old right here earlier, and this is how it came out. And at both of these targets, these are the only targets where the two divisions work together, because the parasympathetic division is going to be in control of the arousal phase of the sexual response, and then the sympathetic division is going to take over for ejaculation. So what this is the genitalia, or we could think, yeah, it's genitalia. And we could say that the PNS is stimulatory for arousal. Okay, I'm going to have to erase this. So I do think I want to finish out this neurotransmitter receptor discussion right now. Because usually in class I can just bounce back and forth between all these figures and it makes it easy. So maybe take a break, take a breath, think about all of these targets and what we've talked about. And now let's think about these neurotransmitters and the receptors that we're going to find at all of the targets of these neurons, just right across the synapse. I'm going to get some water. All right, so neurotransmitters have to bind to neurotransmitter receptors. And what is going to determine whether you have a stimulatory or an inhibitory effect at the target is the receptor subtype at the target. We're not going to worry about receptor subtypes. We're going to worry about large classes of receptors. Okay? Why? Because that's what we're going to do. These are cholinergic neurons. Preganglionic neurons that are cholinergic neurons and postganglionic neurons that are cholinergic neurons, which means that they're releasing acetylcholine, which means that across the synapse we must have an acetylcholine receptor. Okay, there are two general classes of acetylcholine receptors, or cholinergic receptors. You already met one. You met the nicotinic receptor at the neuromuscular junction, at the motor end plate. The nicotinic receptor gets its name because it also binds nicotine. The muscarinic receptor, that we're going to talk about in a moment, gets its name because it also binds the mushroom toxin muscarine. So other chemicals can bind these receptors, but this is what the name we're giving them. Nicotinic receptors at skeletal muscle. What happened when acetylcholine bound? It was always excitatory, right? Nicotinic receptors are always excitatory. So, cholinergic receptors, we've got two types, nicotinic and muscarinic. Okay, nicotinic receptors are always stimulatory. So anywhere I've got a nicotinic acetylcholine receptor, then when acetylcholine binds it, I will cause stimulation of that thing. So in this case, all of my postganglionic neurons have nicotinic cholinergic receptors, which means when my preganglionic neuron releases acetylcholine onto it, it's going to stimulate that neuron to fire an action potential. This is also a cholinergic neuron, which means that it's going to release acetylcholine that will bind a cholinergic receptor. But now at our targets, it'll be a muscarinic receptor, and the effect will be stimulatory or inhibitory depending on the subtype at the target. Okay, so nicotinic, always stimulatory. Muscarinic, stimulatory or inhibitory depending on subtype, and we're going to leave it at that. Subtype where? At the target. What does this mean? That the only location in the body or in our autonomic nervous system that I have muscarinic cholinergic receptors is on targets of my parasympathetic division. Okay, so muscarinic receptors, these are found on PNS targets. Well, what you're going to see in a moment is that most of these targets are exactly the same for the sympathetic nervous system. Well, how is it going to tell which is being activated? Well, because of the receptor. The sympathetic nervous system isn't using acetylcholine here. It's using a different neurotransmitter. It is using acetylcholine here, so let's talk about that. Cholinergic receptors, nicotinic receptors are found on all postganglionic neurons in both divisions, in the parasympathetic division and the sympathetic division, and in skeletal muscle. So nicotinic cholinergic receptors, these are on all postganglionic neurons. They are on, so in both divisions, PNS and SNS, and they're on our skeletal muscle at the motor end plate. And they're always stimulatory. Okay? So you get a command to salivate coming down your cranial nerve. You release acetylcholine. You stimulate an action potential in the postganglionic neuron that's synapsing at my salivary gland and will release acetylcholine that's binding to a muscarinic receptor and will cause salivation. Okay? So you release acetylcholine, or you stimulate, let's say I need to decrease my heart rate because I just got all excited for no reason. Then I need to send this action potential down my vagus nerve, which will cause acetylcholine to be released into the synapse. It'll cross and bind a nicotinic receptor on my postganglionic neuron that is going to release acetylcholine onto the wall of my heart and decrease my heart rate. It's going to bind a muscarinic receptor and decrease my heart rate. Okay? Cholinergic neuron, cholinergic receptor, nicotinic cholinergic receptor. Cholinergic neuron, cholinergic receptor, muscarinic cholinergic receptor. Okay? That's how it all comes together for the parasympathetic division. Let's check out the sympathetic division. Grab some more water. You should too. As I was erasing this, I realized that the more complete picture would be to leave it up and draw everything else on top of it, because it's all happening at the same time in your same body. However, that makes a very illegible picture. This one is already illegible. It would be even worse if I drew it on top of it. But before I erase completely for a moment, let's just imagine here are these sacral nerves I was talking about. Here are these cranial nerves I was talking about. Well, now I'm going to start talking about my thoracic and lumbar nerves that are coming out and meeting in my autonomic ganglion, and then the postganglionic neurons that are hitting these exact same targets. So it is a hot mess in your body all over the place. So be aware of that. We're going to pull back and pull away from the parasympathetic division, but it's still there. And the two are working in this dynamic antagonism to keep you alive and in homeostasis. All right. So I know it looks like mumbo jumbo, but work with me, people, we can see it. So the sympathetic division arises from the thoracic and lumbar spinal cord. So it's our thoracolumbar division. We said that there was still not a cameraman telling us to plug in our camera. We said that the preganglionic neurons in our sympathetic division were going to be short because they are all synapsing on their ganglia, which is in the sympathetic trunk. So a ganglion, again, has the cell bodies or somas of our neurons. So here now, our anatomical differences is that we have short preganglionic neurons, which means if we've got short preganglionic neurons, then we must have long postganglionic neurons. Okay, so we'll put that here for now. So we've got short preganglionic neurons, and they are synapsing onto our long postganglionic neurons in the ganglia, which is part of the sympathetic trunk. or the sympathetic chain. So you'll see, I like sympathetic chain ganglia because it's like a chain gang, but it's a chain ganglia. So this is the sympathetic trunk or chain. Different books use different names, and that's where our ganglia is. So all of our preganglionic neurons are short, and they're synapsing onto our long postganglionic neurons in the ganglia, which is at in the sympathetic trunk. But you're like, wait a minute, there were three different pathways. Is it at there? Well, I mean, we could go up, we could go down, we could go to a collateral ganglia, or we could do what happens right here at the adrenal medulla and just send one really long preganglionic neuron there to cause its effect. Okay? So let's talk about neurons and receptors and effects. Okay. Our preganglionic neurons are what? I told you all postganglionic neurons had acetylcholine receptors, nicotinic, which must mean that these preganglionic neurons are also cholinergic. I hope that I said that. I probably did. Our preganglionic neurons here are cholinergic, meaning that they produce, store, and release acetylcholine into the synapse. So I'm synapsing here in my sympathetic trunk on my postganglionic neuron that must have an acetylcholine receptor, and now this neuron is extending away. I'm just putting it here because we'll go over each in a minute. Easiest for my brain at the moment. So right here, if this is a cholinergic neuron, it must mean I have a cholinergic receptor right here, and I do. But this is not a cholinergic neuron. This is an adrenergic neuron. The neurotransmitter that's released from our postganglionic neurons is norepinephrine. So my long postganglionic neurons are what we call adrenergic. So in the sympathetic division, my postganglionic neurons, sure, they're long, but they are also adrenergic. Adrenaline, adrenergic, adrenal, adrenergic. So adrenergic, this means that these neurons are releasing what's called the neurotransmitter called norepinephrine. So our postganglionic neurons are adrenergic, and that is because they produce, store, and release the neurotransmitter norepinephrine, which is abbreviated NE. So these are adrenergic, and what they are storing in their little synaptic vesicles is NE, norepinephrine. Okay, so let's talk about the effects of the sympathetic division at each of our targets, and then we'll come back and review the neurotransmitter thing again, okay? We're putting this in our back pocket for now, knowing that this is a cholinergic neuron, which must mean that this has a cholinergic receptor. This is an adrenergic neuron, which must mean that this has what type of receptor? Adrenergic. We'll get there. Okay, let's think about our targets. So, the role, what happened to pupils in an emergency situation? They dilated real big, right? So that we could let in as much light information as possible and retain as much information as possible about that emergency situation. What happened was visual acuity went down if we didn't train it, because now all of a sudden we're exposing all of the rods in the periphery of our eyes. So we're occupying all of that neuronal territory and energy, processing a lot more information. When we're in a fight or flight situation, our pupils dilate. So we stimulate pupil dilation, our visual acuity goes down. We inhibit the secretions of your nasal and lacrimal glands, so you're going to get dry. You're going to inhibit your digestive salivary glands. So we'll inhibit digestive salivation. What does that mean? I thought, well, isn't all salivation digestive salivation? No. Right now, I'm salivating so that I can try and keep a semi-wet, moist mouth so that I can talk without my lips sticking to my teeth. I'm only moderately successful. Again, I have a swamp cooler, not central air, so I'm pretty hot, but still, like, I'm salivating. Well, if I were to go grab some Cheetos, then I'd start a different kind of salivation, a digestive salivation. When I'm in a sympathetic division situation, I'm going to inhibit digestive salivation. But I know that you've all been in these situations where you've got like a speech to give, and you're like, I got this viscous, thick saliva. You're getting nervous. I gotta talk to my boss. I have been thinking about why this happens, and I think it's because if you get really, then you're more likely to drink some water. And if you drink some water, you're going to increase your blood volume, which is going to increase your blood pressure. And when you're in a fight or flight situation, guess what you need to do? Increase blood flow and increase blood pressure. So that's going to happen. So that's the only thing that I can figure out as a physiological effect. So as far as, and I bring that up because last semester I had a student say, but I read in the book that we stimulate specific like salivary secretion of thick viscous saliva when we're in a sympathetic. It's true, we do, but we inhibit digestive saliva. So for our sympathetic division, you could think that we're going to inhibit digestive salivation, but we could stimulate the production of a thick saliva. And you'll see we've got different types of salivary glands. They're intrinsic to your oral mucosa and extrinsic, actual different organs. And we'll meet all of them next semester. So this is how we can get different salivas. Okay, cool, perfect. Okay, this bad boy right here is your skin. So this is an example where we don't have the same targets. We didn't talk about skin at all in the parasympathetic nervous system, because the skin's not really involved in resting and digesting. What could the skin be involved in a fight or flight situation? We've already talked about the integument as an organ. You could stand your hair on end, right? And like get bigger, like cat fight, like cats do, right? So that's one thing. We can stimulate our erector pili. But the other thing that we can do is we can turn on our sweat glands and we can vasodilate if need be, if we're getting super hot and stuff, to bring body temperature away. Now, this is another thing that I know you've probably all experienced, especially if you've got to like get up and give some speech in front of 250 people and you don't like speaking in public. I don't like speaking in public. In class, I probably talk faster than this because I'm nervous. Now I'm like speaking in the public of my living room. It's awesome. But in class, like my hands get real sweaty, right? I start dripping sweat. Why? Because this is a target of the sympathetic nervous system. If I'm in a fight or flight situation, then I'm going to start sweating. And it's going to help to take this body heat away, because you'll see, like if you're fighting or fleeing, you're going to be producing a lot of body heat. We can't go above body temperature, so it's going to want evaporative cooling will be important, but also that defensive mechanism of the erector pili. So what this is the skin, and if we wanted to think about specific effects of the sympathetic nervous system of the skin, we could say that it's stimulating our erector pili and our sweat glands. Okay, at the heart, if you're in a fight or flight situation, what do you think you need to do? Increase or decrease heart rate? We're going to increase it. All right, the other thing here is that we can actually increase the force of contraction so that we can squeeze more blood out. Okay, we'll talk more about that next semester. At the lungs, we'll increase our respiration rate. Now, if you've ever heard of an EpiPen, this is what an EpiPen is doing. Epinephrine is what's released from your adrenal gland. And so it will synergize and amplify all of the effects of your sympathetic nervous system. One of those is it will stimulate bronchodilation, so you can breathe. If you've ever heard somebody's having an anaphylactic reaction, anaphylactic shock, what's happening is they're bronchoconstricting and they cannot breathe. You give them an EpiPen and they're good. Okay, well, norepinephrine binds adrenergic receptors just like epinephrine does, and will stimulate bronchodilation. Okay. So at the lungs, increased respiration rate, increased bronchodilation. At the stomach, I'm going to inhibit motility and secretion. At the liver, I'm going to inhibit secretion, but I'm going to stimulate the breakdown of my stored glycogen. I'm in a fight or flight situation. I need glucose to fight and flee. So at the liver, I could stimulate glycogenolysis. Always look at words. Glycogenolysis. Lysis, breakdown. What? Glycogen. Glycogenolysis. Sympathetic nervous system can stimulate glycogenolysis. This is my spleen. I can stimulate my spleen to eject its stored red blood cells. So it would be stimulatory there. And then I've got more blood pressure. I can do more stuff. At the intestines, I'm going to inhibit secretion and motility. At the urinary bladder, I'll inhibit micturition, the reflex. I could lose parasympathetic control and void, different. And at the reproductive organs, now the sympathetic division is going to work cooperatively with the parasympathetic division. And here, this is control of orgasm in females, which is ejaculation in males, and then the resolution phase in males that females don't have. Okay, so those are the effects at the targets. Let's quick review neurotransmitters, receptors, and get through this. How does all this relate? We've got the short preganglionic neurons that are cholinergic, that are synapsing onto long postganglionic neurons that are adrenergic. So that means that we're using both cholinergic and adrenergic receptors in the sympathetic division. Whereas in the parasympathetic division, we only used cholinergic receptors. So let's look at this. Here we've got receptors again. And we must have cholinergic receptors on our postganglionic neurons because our preganglionic neurons are cholinergic. And the ones that we have are nicotinic. So here, we've got nicotinic, which means they are what? Stimulatory or inhibitory? Always stimulatory. So receptors, I've got nicotinic receptors on all postganglionic neurons. So that when my preganglionic neuron releases acetylcholine, it can bind my nicotinic receptor on my postganglionic neuron and have a stimulatory effect, which means my postganglionic neuron is going to shoot an action potential that will result in the release of what? Norepinephrine, because these are adrenergic neurons releasing norepinephrine, which means that my targets must have adrenergic receptors. So for receptors, I also have to have adrenergic receptors. And there are different subclasses again. We've got alpha and beta, 5 subclasses of adrenergic receptors. And these are going to be able to bind both epinephrine and norepinephrine with varying kind of, or that each receptor has differing affinity, which means that when I dump norepinephrine on as a neurotransmitter, it can have one effect, but then when I start flooding the system with epinephrine as a hormone, it can bind to a different receptor and amplify the effect above and beyond what's happening because norepinephrine is interacting with its receptor. We've got alpha and beta receptors, and these are going to be either stimulatory or inhibitory, depending on which one we have at the target. Okay. So for example, you might have heard of beta blockers and people with hypertension. They take beta blockers. That's blocking a beta adrenergic receptor here so that we can decrease the heart rate and force of contraction because this person has hypertension. So we need to block the effects of activating that receptor, okay? So in our sympathetic division, we've got cholinergic receptors on all of our postganglionic neurons. They're nicotinic cholinergic receptors. They are stimulating an adrenergic neuron to release norepinephrine, which means that I have to have an adrenergic receptor on my target. There are 2 general subclasses of adrenergic receptors, alpha receptors and beta receptors. That's the nitty-gritty you need to know. And they will be, when bound, they will be stimulatory or inhibitory depending on which one is at which tissue. So this is how it's possible. I could be stimulatory to increasing heart rate and force of contraction, but be inhibitory to motility and secretion in my stomach. Okay? Okay. I think that wraps up pretty much all of it. I'm going to erase this board. We'll quick go through the rest of the slides and make sure we're good. I can't quite express to you how glad I am that we already talked about neurotransmitters. I have to take a class in 13 minutes, so one could say maybe my fight or flight system is activated as I have to race through lecture. No, it's not. Which division of the autonomic nervous system would that be? It would be the sympathetic division. All right, neurotransmitters. These are released by neurons, right? And they are going to cross the space called the synaptic cleft, and they're going to bind to some effector. Okay, so neurotransmitters are released by neurons. These are chemical messages that are crossing the synaptic cleft and binding an effector. So we've already talked about other neurons as effectors. We've talked about preganglionic neurons, postganglionic neurons. We've talked about skeletal muscle as an effector of a lower motor neuron, and now we've talked about the effectors in both branches of the autonomic nervous system. The eye, the pupil, the lacrimal glands, the nasal glands, the salivary glands, the heart, the lungs, the stomach, the spleen, all of that. So, all right. The effectors then for our autonomic nervous system are cardiac muscle, smooth muscle, and glands. And neurotransmitters are the chemical messages that are going to be conducting our signals through the system. So, neurotransmitters. Our cholinergic neurons release the neurotransmitter acetylcholine, which is abbreviated ACH, and this we said we find at the neuromuscular junction where it's always stimulatory. Acetylcholine is also released from all of our preganglionic neurons in the autonomic nervous system. So acetylcholine is coming from our lower motor neurons at the neuromuscular junction and from all of our preganglionic neurons in the autonomic nervous system. Okay, so that's what we're using in our somatic nervous system and what we're using in all of our preganglionic neurons in the autonomic nervous system. Furthermore, our parasympathetic division is going to use it in all of its postganglionic neurons. So acetylcholine is also coming from all parasympathetic nervous system or parasympathetic division postganglionic neurons. Okay, cool. Norepinephrine is coming. Only in this case, all we're going to worry about is norepinephrine as the neurotransmitter that's coming from our postganglionic neurons in the sympathetic nervous system. So this is coming only from all of our sympathetic nervous system postganglionic neurons. Okay, cool, wonderful. So we've already also talked about our receptors to some degree. So cholinergic receptors are going to be able to bind to acetylcholine, right? Acetylcholine, cholinergic receptors. So we've got two types of acetylcholine receptors, cholinergic receptors, nicotinic receptors, and muscarinic receptors. Let's have a quick question, review of this in your mind. Where do we find nicotinic receptors? On all postganglionic. I'm I can't even with a microphone or anything anymore. It's all the last day of class. So, cholinergic receptors bind acetylcholine. Nicotinic receptors are found on all postganglionic neurons. Muscarinic receptors. Okay, what does this mean? That in both divisions we have cholinergic preganglionic neurons releasing acetylcholine that's binding to nicotinic receptors on all of our postganglionic neurons, whether those neurons are cholinergic neurons or adrenergic neurons. Both types of neurons have nicotinic receptors, so they will respond to acetylcholine, fire an action potential that will cause them to release their neurotransmitter. Muscarinic receptors are also going to bind acetylcholine. These are only found on our parasympathetic nervous system targets. So, sympathetic nervous system can't have an effect here because our targets of the sympathetic nervous system, the postganglionic neurons, are releasing norepinephrine. Not going to bind to a cholinergic receptor. Okay? Cool. So, muscarinic receptors are on all of our parasympathetic nervous system targets, and these are either stimulatory or inhibitory, depending on the target and subtype. Nicotinic receptors are always stimulatory at the motor end plate and at the receptive segments of our postganglionic neurons. Okay. The other type of neurotransmitter receptor then that we have is an adrenergic receptor. Again, we have alpha and beta adrenergic receptors. Not going to make you worry about memorizing all of the specific different types at the different targets, but the reason that we can have like stimulation at the heart and say inhibition at the stomach is because we have different receptors there. So norepinephrine and epinephrine both bind. So norepinephrine is going to be the neurotransmitter that's released from our postganglionic neurons onto the target. Epinephrine is released from the adrenal medulla and enhances the effect because it binds to adrenergic receptors. So one thing that we could say is that epinephrine from the adrenal medulla, and this is going to be important next semester and just all the time, epinephrine from the adrenal medulla is synergistic to the SNS. Or to sympathetic nervous system activation. What does that mean? That if all you have is norepinephrine on board, you will increase heart rate. If all you have is epinephrine on board, you'll increase heart rate. But if you have both epinephrine and norepinephrine on board, you will increase heart rate above and beyond additive. So they really amplify the effects. That provides a good segue into talking about interactions at all. How do the two divisions of the autonomic nervous system interact in the body? Well, mostly they're antagonists. So that means that when one does one thing, the other undoes it. So if your sympathetic division increases your heart rate, your parasympathetic division brings you back down to rest. So they have the opposite effects at target tissues. So we'll say most of the time, or at most targets, they have the opposite effects. And what this does is allows for this interaction that's like what we call dynamic antagonism. Antagonists are opposites, they kind of oppose each other, but dynamic is the ability to like be changing and express dynamism. So dynamic antagonism is what these two systems display as an interaction to keep you in homeostasis. So dynamic antagonism keeps you in homeostasis. What does this mean? Well, if I have to be in this changing situation of turning on and turning off, well, right now, I just had lunch, so I'm like digesting and all of my blood flow is like under parasympathetic control and it's going to my visceral organs and I'm secreting gastric juice and my stomach's getting activated, this new muscle there. So that's really going on. Okay, I'm like, rest and digest, I'm ready for a nap. and then like bang, 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 somebody bangs on my door, it's going to alert me. And now I'm going to have the antagonistic, exactly opposite response. I'm going to shunt blood away from my digestive organs to my heart. I'm going to increase my heart rate. And so this is like dynamic because it's changing, because then I realize it's just the delivery guy who could have been a little more polite. And you know, I'm sure you can come up with some adjective to describe him. And so then he leaves, and I realize then this dynamic antagonism will bring me back. Then my parasympathetic nervous system is going to kick back on and bring my heart rate back down, and then I'm going to take my nap. So dynamic antagonism, dynamic is changing, and antagonism is like opposite or opposing effects. And basically they like work. This one will turn on and this one will turn off, and then this one will turn on and this one will turn off, and like to keep you in this state of homeostasis so that you can change and keep like in this relatively stable environment despite whatever may be going on around you. I'm not going to write anymore, I'm muted at that. Parasympathetic and sympathetic tone. So just as you have some level of skeletal muscle tone that allows you to maintain your posture even if you're falling asleep in the front row of your class, you also have sympathetic and parasympathetic tone that allows for the quick movement of blood and things. So if we look at like baseline level of contraction or activation of the sympathetic nervous system, the sympathetic nervous system, it has always like this baseline level of tone in our blood vasculature or our blood vessels, which means that if I'm like have a lot of blood in my digestive tract because I'm in a parasympathetic situation, because of the sympathetic vasomotor tone, if I all of a sudden need to quickly constrict and shunt that blood away from my guts, I can do it because my sympathetic nervous system has the tone in my blood vessels. Parasympathetic nervous system tone is generally in control of what's going on in, like setting and helping to give tone to your digestive organs and things like that. So this is more control of viscera. Okay. The only time the two systems really cooperate is in the sexual response. And so for the cooperative effect, we could say they are cooperative in the sexual response. And the sexual response, you can break it in 2 or 3 phases, depending on whether you're talking about male or female. For everybody, there's an arousal phase. And that's in control, under the control of the parasympathetic nervous system. So during arousal, what's going to happen is what does the parasympathetic nervous system do? We said it was secretory and kind of wet and juicy. Well, during the arousal phase, it's going to get the bulbourethral glands going in the male genitalia so that we can release bulbourethral fluid and neutralize the acidity of the urethra and lubricate the penis. In the females, it's going to activate our greater vestibular glands and allow for the release of vestibular fluid onto the vestibule to lubricate the vagina. And it's also going to change blood flow to the area so that both erectoral bodies can engorge. So during this phase, we could say it's going to stimulate secretion of our accessory glands, but it's also going to stimulate a change in blood flow so that we can get erection. And then females do have erectoral bodies, so the male erectoral body is, well, it's 3 erectoral bodies in the penis. The female erectoral body is the clitoris, so both of those things are happening in the arousal phase under control of the wet and juicy parasympathetic nervous system. The sympathetic nervous system is in control of things like what? Increased heart rate, increased respiration. This is in control of ejaculation in males, which has 2 phases we'll talk about next semester. It's orgasm in females. And then in males, there's an additional 3rd step, which is resolution, and that is also under control of the sympathetic nervous system. Now let's think about what we just talked about, the things that the sympathetic nervous system did. What did it do at heart? It increased heart rate and force of contraction. What did it do at the lungs? It increased respiration rate, right? Well, at ejaculation and orgasm, guess what males and females experience? An increase in heart rate, increase in respiration rate, widespread actually increase in skeletal muscle contraction. So you've got some somatic nervous system activation as well. So that is when they cooperate, and we will go over that in greater detail next semester. As far as the control of the autonomic nervous system goes, the autonomic nervous system is under the control of our higher brain centers. So ultimately, your cerebral cortex is like the big boss of everything. Well, what does that mean? It's not going to like stop your heart rate. The hypothalamus is the big boss of the endocrine system and autonomic nervous system. So the hypothalamus is kind of paying attention to everything that's going on in all of your viscera and deciding what to do. What this part here means, like the cerebral cortex part means, is like if I'm having a panic attack because I see a spider on the floor and my heart rate increases, I can realize with my cerebral cortex that I'm big enough to squash that spider. And I have nothing to be afraid of. My cerebral cortex can override that sympathetic nervous system activation through my hypothalamus, which is going to send the commands through my brainstem and spinal cord, and down and out through which nerve? The vagus nerve would be bringing the command out to lower my heart rate. Okay, that was kind of unfair because I thought you didn't have to worry about the nerve so much. But I guess I should have said through which division. Parasympathetic division would then bring me back down to a normal heart rate after I've squashed the spider. So, the autonomic nervous system is under central nervous system control. The first and primary regulator is the hypothalamus. And so one of the things that can help people remember this is that the hypothalamus really controls the 4 F's. Fighting, sympathetic nervous system. Fleeing, sympathetic nervous system. Feeding, parasympathetic nervous system. Reproduction. Ooh, that's both the sympathetic and parasympathetic nervous system. And you say, lady, how is that R and reproduction an F? And I say, figure it out. I believe that you can. So, yeah, the main controller of our autonomic nervous system is the hypothalamus. I mean, you can think about like your basal heart rate is set in the heart. Your basal respiration rate is set in the medulla oblongata. Your pons can control that. If anything's wonky down there, hypothalamus can kick in and say, hey, you need to do something. And then that command is going to go down here, hey, we need to do something. And then that's going to come out through one of our various nerves, depending on which branch we're talking about. If we're talking about the parasympathetic branch, where are the nerves going to come out of the spinal cord? Cranial nerves and sacral. If the branch that we're talking about is the sympathetic nervous system, where's that going to come from? Thoracic and lumbar. Okay? Okay. Yes, beautiful. We got this, people. So, yeah, there's still going to be a review of that somehow. So stay tuned. Don't worry too much. I would study the figures that are already erased, and I would just try and think about like general rules. Maybe another thing I would do is think about like pre and post ganglionic neurons. So if this is a cholinergic neuron, then what type of receptor must be here? Cholinergic. Specifically, if this is the preganglionic neuron, postganglionic, then this is the nicotinic. Okay, then, alright, well, what type of neuron is this? It depends on what branch we're talking about, right? If it's the parasympathetic nervous system and it's postganglionic, what type of neuron is this? Cholinergic. If it's the sympathetic nervous system and it's postganglionic, what type of neuron is this? Adrenergic. Okay, so then it's going to change the receptor type here. We'll have a review. Go take a breather. See you soon.